So welcome everybody, thanks for coming over. My name is Valentina Alaria and I've been at PLUMgrid for about 3 years, so pretty much from the beginning of the company. So what I'm going to do tonight is talk a little bit about OpenStack networking and then what PLUMgrid does, which clearly fits within the realm of OpenStack networking and that layer of the stack there. So before I start, I think for the benefit of myself and Josh, can I get a quick show hands of people that have been already installing OpenStack and have an understanding of the networking layer? Somebody? All right. So I would say 50% do understand that layer and 50% are pretty new. So what I'll try to do, just to bridge the gap for those that are new, I'll go through some of the basic concepts without spending too much time, just to get everybody to kind of get to the same level. And then we'll talk a little more about some of the advanced topics and show what PLUMgrid does in that space. I have about an hour, right, 40 minutes?
Yeah, you do.
Okay, that's okay. All right, so first of all, let me start with the story of the name PLUMgrid, since it was just talking about it. It's a very geeky story, so pardon me if I go very technical there, but so the idea of PLUMgrid is that when the company was started, we wanted to create something that could really transform how networking is delivered to the users. Not just a point product, but a big vision for a platform that could take customers through the next 15 years in terms of services and functions that would need to get delivered on that software layer. And so the idea is that we wanted to create a data plane that was very flexible, programmable, and extensible. It could handle any type of traffic and any type of problem. And so the idea is we took, we looked at what the basic operations that are needed on a packet are, and those are 4. And it's the ability to parse, look up, update, and modify, and that's the plum. And that, in a cloud environment, you want this flexible, programmable data plane to be fully distributed, and that's why it's a grid. So PLUMgrid, that's kind of the story of the company name. And you see, as we talk about what we do, PLUMgrid is a software-only product that provides virtual network infrastructure for OpenStack. So if you're familiar with the OpenStack architecture, we come in next to kind of the compute layer, the storage layer, and we provide connectivity for virtual machines, as well as other form of compute units like bare metal or containers, whatever else you have out there. And we enable multi-tenant kind of solutions on top of OpenStack. But let's start from the beginning and look a little bit at the architecture of OpenStack and why it's relevant. So, obviously, why are customers looking at OpenStack? I shouldn't be telling this crowd. You all are obviously here for a reason. You probably are either on the customer side looking at how to transform your own infrastructure, or if you are a vendor or a solution provider, you clearly understand that there is a need for a transformation of how infrastructure is delivered. And obviously, we see OpenStack being well positioned to achieve and enable this transformation. This one slide, again, not necessarily for this crowd, but clearly shows some of the stats around OpenStack and the amazing growth that we're seeing in this community. How many of you were at the last summit in Paris? Well, if any of you, not many, but if any of you have been at that summit and also some of the previous ones, you could probably witness the amazing transformation and the complete, growth that we have seen in the community, going from a few, 50 people 4 years back to 6,000 or so attendees in Paris. So certainly this community is growing, and we see, which is very important for us, we see a larger number of use cases being built on top of OpenStack. And I'm very pleased that kind of the follow-up to my presentation is going to be around platform as a service and what Cloud Foundry enables on OpenStack, because that's one of the major applications and use cases for this platform. Now, when you look at building an OpenStack cloud, there is one component that happens to be kind of the junction of everything, and that's the network. The reason why it's at the junction of everything is because that's how you really provide connectivity. You provide connectivity between compute elements, you provide connectivity to your storage infrastructure, and it's also how you provide isolation. So there's these two contrasting requirements of enabling entities to talk and exchange information while providing a very secure, isolated, multi-tenant sort of infrastructure. And at the same time, again, you want to be able to reach your storage infrastructure, which is often shared and something that multiple tenants can leverage at the same time, and provide some multi-tenant solution for your compute layer. So we'll talk a little about some of the requirements for the network infrastructure, and I'm going to start from a very generic, high-level point of view. I don't know if the slides look that good, but you guys at least can see. But the idea here is that when you, as a user of OpenStack, start playing with this architecture and this technology, you should consider the network infrastructure architecture as a fundamental piece of your design. So the claim that we make is that regardless of the choice you end up making down the road, the initial consideration of which architecture is right for your environment, it's fundamental. The network plays a very important role, and if you choose the wrong architecture from the start, it might be something that satisfies the requirement of a very small initial deployment. We see a lot of users starting from 5 servers, 10 servers, but what you need to look at is what's the end goal of your deployment. Are you looking at growing beyond that very small initial installation and going to multi-racks, multi-sites? So those are hopefully some talking points for you, internally within your organization. I was just talking to some of you as users who are just getting started in evaluating OpenStack and understanding how to use it. So this is meant for you to have a conversation internally within your teams and start discussing what are the requirements that our organization has for the network infrastructure layer. So if you look at this slide, it goes from the performance. The performance is, it's an interesting conversation to have. Lots of things are changing in the way the network gets delivered in OpenStack, and we'll talk a lot about how PLUMgrid, as an example, brings networking software. So when you come from a more traditional networking background of the network being physical boxes, the concept of performance changes. And that's something that you need to, again, evaluate internally and understand what type of application am I running? Do I need a solution that can just provide some basic feature and functionality and those can run as a VM somewhere so I can maybe get a gig out of it? Or do I need something that can scale with my infrastructure and perform with my infrastructure, giving me tens of gigabit of throughput? So that's kind of the first bullet up there. The second consideration that you have to go through is from a scalability perspective. Are you going to start with, right away a very large deployment? No, as I said earlier, a lot of you are probably going to start from a handful of servers. But again, what's the growth and what's the path of your deployment moving forward? The network, it's something that it's actually quite tricky to extend beyond a handful of servers if you don't think it through properly. And so again, do you want the ability of going beyond a single rack? Do you want the ability to go beyond a single OpenStack cell, OpenStack kind of installation? The third point here is high availability. Again, the network model changes quite a bit. It becomes software. It becomes integrated within OpenStack. And so when you look at how your network is highly available and is resilient to failures, you need to start considering different components that are not commonly what you would consider on a physical infrastructure. So you need to look at, is my control plane resilient? Is my data plane capable of tolerating failures? How do I interact with a failure of OpenStack, per se, of the main cloud management system? And then the fourth bullet, it's a very interesting one, and this is something where we spend quite a bit of time, Kelly, myself, and Fernando, which are the other two PLUMgrid members here, spend quite a bit of time on the road talking to customers, and a lot of them tell us that, hey, OpenStack looks great, there's a lot of adoption out there, but hey, I'm a cloud provider, I'm building a service on top of OpenStack, and I want to be competitive. And so how can I choose components that give me an edge, give me the ability to build advanced services and grow and change as the needs of my users evolve? So again, as you look at the OpenStack architecture and how you can leverage different vendors underneath. OpenStack was really built for this extensibility. From the beginning, it's this modular architecture where you can leverage different plugins, different components. And as vendors in the OpenStack community, we see a big need for the ability to differentiate beyond the very basic set of features that are commonly present everywhere. Is there any question? Please jump in, make it interactive. I'm not here to talk to myself for an hour, so hopefully somebody has some thoughts they can share. But this was again the reason I wanted to share this is to use it as bullet points when you discuss internally. Hopefully it's something that can help you in your evaluation of the network layer vendors and options that are out there. And if anybody has gone through a selection of a vendor, I would love to hear if those are the criteria you applied for your choice or not. Anybody wants to share their experience? You're quiet. Wow. All right. More beer? Alrighty, so since a few of you were brand new to OpenStack and the networking architecture, I'm going to touch a little bit of how it actually works and how it's designed. Hopefully I'm not going to bore the ones that do understand how it works. So clearly OpenStack has multiple components, and those of you that are familiar with the community have seen this graph and the next one. But this is just to show that there is multiple pieces that work together. And those are some of the kind of initial big building blocks. If you're familiar with the evolution of the community and all that is happening, especially in the last summit, there's now a proliferation of what are called projects and kind of core components of OpenStack. So this is really by no means an exhaustive picture of all the moving parts that are now present in OpenStack. But when we talk about the network component, and we're also going to show you a quick video. Fernando will jump into the presentation later on and show you kind of a quick demo of how it all comes together. But the components that are relevant for this conversation are always the interaction between the network and the compute piece. And then as we talk, Josh will cover some of the PaaS infrastructure. You see obviously the storage and the API layer, how it all comes together. But the network piece was originally, and I'll show you this very scary picture, was originally part of the compute component. This is Nova. This is a very old picture representation, which now has been obsolete. Actually, it's completely different. But the reason why I like it is because it shows where networking used to be. So when it came out, it was a very small component of Nova, so the compute part. Now, what happened down the road is that as users started leveraging OpenStack and building applications on top of it, they figured out that Nova was not quite as capable as they needed it to be. So Nova was really meant to provide extremely basic connectivity, network connectivity between compute nodes. It was not meant to satisfy advanced multi-tenant, rich topology kind of requirements. So that's where Neutron came into the picture. And if you were at the last summit, there were quite a bit of conversations around how do we actually get some of the large deployments that are out there that are running on Nova to migrate over to Neutron. So there's a big discussion going on around how do we obsolete Nova and how do we create a migration path out of Nova into Neutron. So what we'll concentrate mostly tonight is going to be around Neutron, but I'll tell you a little bit about kind of a comparison of what you can do with Nova and why you should, why you could consider Nova as a solution for your deployment, and why you should consider Neutron for anything that is more, again, complex and advanced in terms of use cases. Now, before we jump into the architecture, I just want to show you a couple of slides and get a little bit of terminology in place, because you'll hear me talk about it, and I want to make sure we all speak the same language. So this is a very ugly, pardon me, I made this, representation of a compute node. If any of you that is familiar with Linux understands that there is a kernel and kernel space and user space. Now, when we talk about the network component in OpenStack, there's kind of a couple ways in which, well, there's more than a couple ways. There's, let's say, 3 big ways in which you can consume networking, in which networking can be made available to the end user. One is you use the traditional physical network infrastructure. You have your Cisco gear, Juniper gear, Brocade gear, whatever you want to have out there. You use that, and what you do through OpenStack is you go and configure and manipulate your physical infrastructure. But what we're going to spend most of our time today is talking about the ability to actually deliver the network in software, what we call the virtual network infrastructure. And when you talk about virtual network infrastructure, the way this gets delivered into the compute node is in two form factors. One is it's a kernel module, so it's a piece of code that kind of gets dynamically inserted within the kernel that provides the feature, the networking feature and functionality directly to the VMs. And these, if you're familiar with Linux architecture, this is kind of the best performant possible way of getting this feature and functionality because it's running the kernel, has no performance implication, you don't need to unpack it up to user space. Another way to consume feature and functionality is instead to run it as kind of as a VM, so in user space. And we'll talk a little bit about both models and why one gets leverage versus the other and what are the implications on your consumption and performance and type of use cases that you can build on top of it. Something else that you hear us talk about, especially when Fernando shows the video, there's kind of two types of networks that you can build with OpenStack. And for the most part, what it's interesting for users is the ability to build tenant networks. So what is revolutionary about OpenStack is that OpenStack enables users of a cloud infrastructure to self-service provision networks. And that's something that has never been possible before. So you have a user that logs into your cloud portal, and they can create their own environment. And they can define that they want these many VMs, and they want these VMs to be connected through some topology, network topology. And on top of that, you can specify which IP addresses you want to assign to these VMs, and what type of security policies you want to apply to those, and how they can connect and interact with each other. And all this, again, is done through this very powerful API layer that OpenStack exposes, or through the graphical interface of OpenStack. And as we talk about what Neutron can do versus what Nova can do, this is where the big difference is in terms of how rich and complex these tenant networks can be, and what level of flexibility you can give to the OpenStack users in terms of being able to define what type of infrastructure they want to use for themselves. And then the other component is you still have an external network, something that is already there, exists, and it's usually something you need to be able to connect to. Example is you want to be able to connect to the internet or vice versa, you want to have a client sitting out there being able to connect to your web server, which sits in an OpenStack lab. And that's where the concept of external network comes into the picture, and the ability to kind of glue together this new world of multi-tenant networks all in software in OpenStack with the existing physical network infrastructure. So when you look at deploying OpenStack and you look at understanding, okay, wait a second, how many networks am I going to have? For the most part, if you leverage most of the Neutron plugin solutions that are available out there, you're going to end up having kind of two buckets of networks. You're going to have your existing physical network infrastructure, and that's again your physical gear, your existing gear that you have purchased, it's in the data center, and it's now in charge of providing kind of connectivity, bandwidth. It's designed to have low latency, high bandwidth, best QoS possible. And then now on top of it, you have this new model of deploying and consuming networks, which is what we call the virtual network infrastructure. And for the most part, most of the vendors out there, including PLUMgrid, the way we bring this new layer is by leveraging what is called an overlay network. And I was just talking to somebody that was saying, these overlay technologies are a little confusing. But the very simple way to think about it is you all understand the concept of a hypervisor on the compute layer. You kind of have your hardware, and you have your VMs on top of it, and you have some form of abstraction layer in the middle, which is the hypervisor, which enables a VM to run on top of any hardware. Think about it in the same, like in broad terms, in the same way here. You have your physical infrastructure, you have some form of software abstraction layer, which is what we call the overlay network. And then on top of it, you have the ability to create tenant networks, which are now completely decoupled from the underlying infrastructure. And that's kind of the beauty of it. Now, why is that beautiful and why is that powerful? Well, I mean, if you're running a cloud infrastructure and hopefully you're being very successful, you have a very large number of tenants coming into your cloud portal, the amount of changes in terms of creating new tenant networks, provisioning new infrastructure, spinning up IPs, destroying IPs, moving things around, it's pretty high. And you want to be able to satisfy the requirements of your users as they come. Now, if every time a new tenant comes in, you need to go and touch your physical infrastructure, that's pretty painful. It's painful and it's dangerous because if you mess up something, there is a very nice error propagation property of the physical infrastructure where you can potentially take down the whole thing. So the power of this model is that you decouple the two, you provision these isolated environments for your tenants in the kind of the software space. Exactly as a VM, it's an isolated unit. And you can assign them to different users. So more and more, when you are a network architect for a cloud, you have to handle these two layers concurrently and understand that properties and behavior of the physical infrastructure and its interaction with the virtual infrastructure on top. Any question on this? This is kind of a critical, pivotal point of the whole conversation. So if it's not clear, I'm happy to expand on this.
Can you explain the two flavors of the tenant network up top?
Yeah, so this is a PLUMgrid representation, and I can kind of give you an idea of why we represent it this way. So PLUMgrid has a very particular technology and solution in this overlay network, and it provides what we call virtual domains. So the way to think about a virtual domain is, think about it as an Amazon VPC or a private data center that you can spin up for yourself. It's a completely isolated environment. It's isolated through VXLAN encapsulation or some form of tunnel encapsulation. And as part of the virtual domain, PLUMgrid gives you the ability to define any arbitrary network topology. So these are just two examples of two virtual domains that you can create through the PLUMgrid product, PLUMgrid ONS. And as part of that, you can define any arbitrary topology. So in this example here, you have two tenant networks, two virtual domains. They are completely isolated. They can have their own overlapping IP space. And on the left-hand side, you have a very simple network. We have just a kind of a bridge, a switch, layer 2 segment. You have some routing and some firewalling functionality. On the other side, you have a much more complex network. We have your switching infrastructure, so two separate subnets with two separate IP spaces, some routing in between, load balancing, and firewalling. And this gives you just an idea of kind of the flexibility of what you can do through the PLUMgrid layer. Now remember, this is all done in software, and we'll talk a little more in terms of where that happens, where the magic happens. But to give you an idea, everything that you do through PLUMgrid, all these switching, routing, load balancing, and firewalling, kind of gets distributed magically inside the kernel. So inside your compute node, we have a layer that we call the IO visor, which is a software layer that sits in the kernel module, that gives you all this switching, routing, load balancing, and firewalling fully distributed. I'll rewind and show you a little more gradually, because this is kind of a leap of faith that I'm asking you to take with me, but this is kind of the idea there.
Can you create peering arrangements between those domains?
You can. You can do all sorts of interesting things. You can have routers that can be used at the exit point of, actually Fernando in the demo has some more advanced routing entities that you can use to have virtual domains to interconnect with each other. So virtual domains are kind of Lego blocks. And inside of virtual domains, the smaller Lego block is what we call a virtual network function, which is the purple icons there. And you can kind of compose them. Thanks. Yeah, so the virtual network functions, which are these icons here, those can be composed in any topology. They can be used to interconnect domains. We actually use, we interconnect virtual domains all the time. When you create a tenant network and you give this tenant network external connectivity, we always have the tenant virtual domain interconnect with kind of an external virtual domain. We can use virtual domains to create the under cloud infrastructure. So virtual domains are very, very powerful, even beyond what OpenStack offers through Neutron. Yes?
That's something you can use to bridge kind of legacy physical networking if you've got you're using VXLAN.
Yeah.
But if you're using VXLAN on physical switches or bare metal servers, is there,
Yeah.
do you have a way that you can bridge that into the SDN environment?
Yeah, so the way PLUMgrid works is we are a software layer that can sit even within a bare metal server. It's just a kernel that sits within, you know, Linux. Sorry, a kernel module sits within your Linux kernel. We can work with partners that have hardware solutions, like hardware VXLAN termination. Like we partner with Arista. It's one of our partners that we publicly talk about, where we can have them provide termination for VXLAN. And again, because it's a software layer, we can sit within your existing ESX environment. We can sit within your new KVM environment. So the idea is that we can stretch this SDN layer across pretty much any of your compute layers and provide this connectivity.
I was kind of looking at it in more in terms of using it with something like Ironic, where you wouldn't necessarily have a hypervisor, you wouldn't have a vSwitch running in a computer node, you know, that sort of thing. You would just have a node hooked up to a switch.
Yeah, absolutely. You could leverage it that way as well. Any other question? Yes.
You mentioned you partner with Arista. Is there some type of integration specific?
Yeah, absolutely. So let me get to the PLUMgrid slide and I'll show you where. But the idea is that any overlay technology is kind of a generic concept. Any overlay technology needs an exit point from the overlay magic world into the physical legacy network. And that's usually what is called a gateway. This is not a PLUMgrid terminology, this is VXLAN common terminology. So this gateway, it's kind of a device that sits in the two worlds. On one side speaks overlay technology, on the other side speaks VLANs or layer 3, whatever your network design is. And so this gateway can be usually a software device, so something that you just deploy as a software image on a server, or it can be a VXLAN hardware capable switch, like Arista, for example, is one of those that have VXLAN termination in hardware. And so in particular for PLUMgrid, we leverage them as one of the options as gateways. So they can kind of translate between the overlay world and the physical legacy infrastructure. Yes?
So would you be able to integrate with any hardware vendor?
Yes, absolutely. As long as they speak VXLAN, we can work with any. Just a matter of customers wanting to one vendor versus the other. And not us being a small startup, so being very conscious of resources. Good.
Layer 2 underlay or layer 3 underlay?
So the fabric can be anything. That's the beauty of it.
Personal opinion. This always
Layer 3 underlay, absolutely. I mean, if you have to design it, layer 3 all the way to the edge, and
it's layer 3 removes the possibility of having loops.
exactly.
It doesn't need to carefully apply, right? You need to reallocate subnets and networks into some network plan. Oh, sorry about that. Yeah, I was saying the layer 3 removes the possibility of any loops and spanning tree, any problems in the network, but you need to carefully plan ahead the subnet allocation per rack, per block, or anything, so you need to do a pre-allocation of all of that. Layer 2, you can just grow it elastically and everything's flat, but you need to be careful with potential loops and anything like that, so there's no choice.
The beauty of those architectures is that you can take what you have and make it cloud ready, so we don't require any changes to the existing infrastructure. And if you're designing new environments, then you can decide to go again with layer 3 if that's, again, as Fernando was saying, the choice. We personally see a lot of customers designing new fabrics using layer 3, but again, it's kind of a personal decision there. All right, so I don't want to eat into Josh time. So very quickly on why was Neutron created, and I'll skip through some slides because we spent quite a bit of time on a lot of things. But what was Neutron created? So Neutron started as a project because, I kind of mentioning earlier, because of the need for a more rich and extensive network functionality. From the beginning, something that was fundamental to the Neutron architecture was to be modular and extensible, and that's something that is very important. What Neutron doesn't do for you, it doesn't force you into a specific network implementation. What Neutron gives you an abstraction layer that you can use so that your compute layer gets some form of connectivity. And then the backend implementation of this network can be anything of your choice. That's the modular plugin architecture Neutron brings. That's where I think there's a lot of confusion. Some people say, oh, Neutron is my network feature and functionality. In reality, Neutron can be extremely thin. If you leverage one of the vendors, it's kind of a very thin abstraction layer that just passes through API call from the OpenStack API layer down into whatever implementation of the network you have underneath. Okay, so this is kind of what these 3 slides talk about, and we'll share the slides so you guys can go through all of it. But the idea is really that it can be, as I said here, extremely thin and just be a pass-through to, if you have an SDN controller, for example, in the backend, it's just going to take an API call that says create network, and it's just going to pass it over to the SDN controller and say, hey, create me a network, create me, a subnet, create me this, router, create this interface between this subnet and this router, and so on and so forth. And again, this is where kind of the confusion comes in. Now, if you look at the architecture, again, there's a very ugly picture that I created, but what is important here is that when you look at the plugin, there is kind of a core set of feature and functionalities that come with the plugin itself that every vendor has to satisfy. So when you write a plugin for Neutron, you have to be able to create networks and create interfaces and all sorts of things. But the beauty of it is that you can also expose some additional functionality through extensions, and those kind of get automatically plugged and exposed through the OpenStack API layer. Again, enabling for differentiation of services and more advanced functionality to be built on top of it. Something that is happening, and I just wanted to mention it, there is a lot of conversations happening, especially at the last summit, around advanced services. So this is something that today, for the most part, is part of Neutron. And some of the services are now becoming independent projects, with understanding that there has to be a better architecture for managing the integration and insertion of things like firewalls or load balancers or VPN devices and so on and so forth. But today, some of those advanced services are implemented in what is called a network node. So I'll show you a picture of that. Let me jump ahead. So the idea is that for specific implementations, let's say you have a very basic Neutron implementation, the feature and functionality can be implemented as agents. Now, mapping back to the slide that I had showed you a while back, where I was showing you kernel space and user space, those agents are nothing but VMs or user space components that can run either within your compute layer or more commonly in what is called a network node. So the way Neutron was deployed, especially at the beginning, was that you would have a few controllers that were running the overall OpenStack infrastructure, and then you would dedicate 1 or 2 or 3 servers as network nodes. And those network nodes were running layer 2, DHCP, layer 3, firewall, load balancing, and so on and so forth on these servers, on these dedicated servers. Now, there's quite a bit of changes happening in Neutron. If you're following what happened with Juno, some of those services are now becoming distributed, are now becoming highly available. And so you'll see a mixed bag of some of those things being centralized, some of those things being distributed within the compute layer. The reason why it's important, again, back to your evaluation of the OpenStack networking solution and what you need to look for when you select a vendor or basic open source components that are out there, is what type of applications do I need, and do I need to be able to scale out all my network services because I have a very large deployment, or can I go by and survive with a network node kind of implementation? So this is showing when you use network nodes, you have some servers that are dedicated to running layer 3 services or firewall services or load balancing services. And so what that means is that every time a VM needs to access those services, the traffic will be finding over to those network nodes. This works perfectly fine for small deployments, works perfectly fine for deployments where performance is not an issue, but this is certainly a question mark for you to answer when you look at am I growing my environment? Do I need to now start worrying about placement of this network node, because that becomes a potential bottleneck? Do I need to scale it out and size it such that it can satisfy the requirement of my growing environment? And so this shows you that the traffic handling can vary depending on the different services. So some of it can be local within the hypervisor, where maybe some of the layer 2 functionality are distributed and available within the kernel layer, and some of the more advanced services are instead implemented in the network node. So again, important to keep in mind when you select a solution versus another. So I just want to spend 10 minutes on what PLUMgrid does and show you how we fit into OpenStack and how we change some of those kind of architectural constraints there. So I already told you these, but just to graphically show you where we fit in the kind of cloud stack, we are a pure virtual network infrastructure player, so we are purely software. We don't manipulate anything at the physical network layer. So we're just a software product that gives you on-demand virtual network infrastructure for OpenStack. We bring this a differentiated concept of virtual domains, which we covered in detail earlier on, but the idea is that we have your physical network infrastructure, we deploy on top of it as an overlay solution. We give you the ability to create virtual domains, so these isolated multi-tenant environments. You can select from the PLUMgrid portfolio of virtual network functions. And you can create as many of those virtual domains as you need for your environment. And we are fully integrated with all the major distributions out there. Some of them it's completely automated, some of them it's a manual install, but you can choose to select any of those OpenStack deployments, and we make sure that you can leverage PLUMgrid within those. So there's kind of 3 pillars of the PLUMgrid architecture. The first one is that it's intrinsically scalable because we built everything to be fully distributed. So all the network functions and services that we provide all reside within the hypervisor layer and are fully distributed and are created on demand depending on which compute nodes need to access switching or routing or security policies or NAT functionality. And I'll show you in the next picture in terms of a physical deployment what it looks like and where these features get inserted. The other component that is important, back to the high availability considerations that I was making earlier on, we designed the architecture such that even if the control plane was to completely die, so if the controller was to completely die for some reason or get completely disconnected from your infrastructure, you will still be able to continue forwarding traffic between VMs. Again, this is based on the fact that all the features are implemented in the kernel. We never have to send packets up to the control plane. And the last bullet is something that you see in the video that Fernando has. We have the ability to not just leverage PLUMgrid components, but to give you the opportunity to insert functions from third party that can be open source or commercial inside a PLUMgrid virtual domain. So these purple icons are all PLUMgrid. The orange icons are from partners. So we've done integration with things like Palo Alto Networks to Quagga and Bayada, and we enable you to integrate these components within a PLUMgrid virtual domain. Why is that interesting? Well, there's a lot of use cases out there. One example is you're an enterprise customer, you have made an investment, you have services already deployed, and you want to make sure you can now leverage them in a cloud environment. Back to your question about peering virtual domains, you want to have specific routing stacks that you want to leverage when you peer virtual domains or provide features to your tenants. You can do so by selecting, for example, Quagga or Bayada as a component as part of the PLUMgrid virtual domain. So the service insertion architecture is something that is very unique to PLUMgrid, and it's a very long conversation as well, so I don't want to necessarily cover it in details, but if anybody's interested, we can certainly take it offline and talk a little more about it. Now, in terms of where things reside, there's kind of 3 components that we deploy. There is a component that we call the IO Visor that sits within the compute layer. There is the same component, the IO Visor, that it's leveraged as a gateway, so to exit from the overlay infrastructure into the legacy infrastructure. And as I said earlier, this can also be something from a partner like Arista as an example. And then we have the PLUMgrid directors. So the directors are purely control plane functionality. It's kind of the brain of the system. It's the one that talks with OpenStack and gets the definition of the virtual domains and based on where everything needs to be connected, makes the magic happen, establishes all the overlay tunnels that are needed for communication between compute nodes. Now, I have one slide which we really like. It kind of shows you where these virtual domains live. So you're a user, you log into OpenStack, you create your virtual domains, your tenant networks. What really happens under the covers is that PLUMgrid is integrated also with the compute layer in OpenStack with Nova. We have what's called a Nova beef driver. So we are aware of the fact that interfaces come up, and we are aware of the identity of these interfaces. So whenever a VM comes up, we capture that event, and we look up kind of the information of the VM. We say, oh, okay, we have VM XYZ. This belongs to Josh, and Josh has created this virtual domain blue. And so based on that VM comes up, in this example in those two servers there, what the system does, it will automatically kind of distribute the entire virtual domain topology down into the kernel. This is, if you have to remember one thing, this is the thing that we do completely differently from anybody else. So we let you completely distribute the entire network infrastructure within the kernel. It gives you kind of the best level of performance and scalability that you can get out there. And it's all event driven. So only when VMs come up, we populate the network infrastructure within the kernel layer. I'm going to pause for a second because this is where usually people ask or have comments. Yes?
So is that opposed to using something like OVS?
So the IOvisor, it's a kernel module that would sit exactly where OVS sits. Think about OVS as a hard-coded data plane that was designed for OpenFlow kind of use cases and was designed to satisfy switching and basic kind of routing functionality. The way IOvisor was designed, IOvisor at the beginning of time is like an empty box. It doesn't have anything in there. And based on what you define in the virtual domain, the IOvisor becomes a switch, or becomes a switch router switch, or a switch router NAT security policies. So what is fundamentally different is that instead of being hard-coded and predefined, the IOvisor is a runtime programmable environment that gives you the ability to load dynamically all the network functions that you define as part of the virtual domain. But conceptually sits exactly within the kernel, exactly as OVS sits. What is different is that it doesn't have a user space component, doesn't have the user space component that OVS has. It's not flow-based, so we never punt packets up to user space to look up a new flow. So it's fundamentally different from an architectural perspective, but from an insertion point, it sits exactly within the kernel.
When you say within the kernel, you don't mean the Linux kernel.
Yes.
Because the portion of OVS that's in the Linux kernel is the data plane, actually switching element. The modern versions of OVS are also designed to work with other data planes, and there are several other options. So OVS itself includes the daemons which support NFV and support the OpenFlow protocol. And that's in user space now.
Yes, that's why I said we do not have the user space component that OVS has. And we do not have it for a variety of reasons. One is, again, because architecturally we're not flow-based. So the reason why OVS has a user space component is because when a packet comes in, it's going to hit the tables that sit in the data path. And if there's an entry for that flow, the flow is going to be processed directly in the kernel space. If there's no entry, it's going to be pumped up to user space, where it gets looked up, and potentially even pumped up further to the controller. And that's why there's a user space component in OVS. From our side, the way this works is that this sits exactly in the kernel, replacing the kernel module that OVS is, and there is no need to send packets to a user space component. The NFV intelligence, the overlay intelligence, the tunnel intelligence, all those things that get communicated down to OVS through OVS DB and all the communication protocols here happen between the IOvisor and the director cluster. Make sense? Any other question?
So there is an IOvisor
In every compute node. Yes.
There was a repeat question.
Yeah, so the story here was asking if there's an IO visor in every compute node, and the answer is yes. So when you deploy OpenStack, let's say there's Mirantis gentleman in the room, when you stand up OpenStack with Mirantis, you're gonna get all the compute components up, you're gonna get your storage component, and as part of that installation, you can get PLUMgrid up, and by getting PLUMgrid up, what happens is you're gonna get the IO visor deployed in every compute node that you have there. And so once you start defining your kind of networks in OpenStack, OpenStack kind of makes it, hides what the backend is, right? So you're gonna just log into the UI and start creating networks, and what will happen in the backend is that this network definition will get to the director, and then the director will tell kind of the IO visors what to implement based on where the VMs are.
Is iVisor also SDN compliant, or uses different types of?
So the question is if the IO visor is SDN compliant. What does that question mean?
Yeah, actually, OpenFlow.
So yeah, so the question is if you're OpenFlow compliant. We do not leverage OpenFlow. So OpenFlow could be an application that gets built on top of our platform, but because we do not leverage OpenFlow as a communication protocol, we don't need that to be in place.
And in general, if I may add something to that, what this architecture tries to get away from is what's called flow-based architecture. So basically the idea that a data plane is just a sequence of matched actions, like a switch. Our data plane is more complex than that. A data plane can be turned into a switch, a router, a balancer, a firewall. We're able to render any networking function directly in the kernel. We can build the entire topology directly in the kernel. So we're not a switch. We pretty much can morph the kernel into any networking appliance and into a series of networking appliances. So we can render, as that picture shows, we can render the entire network there. So your packet comes out of the virtual machine and it will go directly through the switch, router, and firewall without leaving the compute node. And when it exits the compute node, it's already been processed through the entire topology. So what we try to get away from is the fact that the network is just a series of flows. We believe that the network is a series of objects, and those objects can be programmed to whatever you want to do with the flows. It's, if you think about how SDN is changing lately, we're changing from the idea that a network is it's a series of flows to consider that a series of objects. So the protocols that are being developed just now, you can look at Upflex from Cisco, you can look at other protocols. Instead of telling a data plane, hey, whatever comes from this port, send it to this other port, what they're saying is, hey, I want a switch, I want a router, I want a load balancer. So that the underlying implementation will create that object however they want to create it. What that allows you to do is creating a stateful network, full network in the data plane instead of moving the state up to the control plane, which is...
So the communication between these objects, does it now become like remote function call, if you think of software, distributed software?
It is. I mean, it's still SDN in the sense that you're separating control plane and data plane. But the misconception that the early SDN approaches had was that SDN is something where you inject directly a flow into a data path. SDN is separating control plane from data plane, making the control plane programmable, right? But that data plane doesn't have to be a switch. And if you think about the first version we were discussing OVS, the first OVS was a simple switch. What happens when you have a simple switch is when you want to do something that goes beyond switching, firewalling, routing, whatever, you need to go to a network node that has a switch, the load balancer. So traffic goes to the network node and back, and up to the network node and back, and you get these terrible hairpins. Now, the new versions of OpenSwitch do distributed routing now. So we have distributed switch, distributed routing. If you want to do that, you still need to go to the network node and back. If you want to do stateful firewalling, you still need to do that. So newer approaches leverage the fact that instead of adding different types of flows to the data plane, you should probably program objects in there. And those objects should be programmable so you can create any sort of object in the data plane. And it's kind of it's like people, instead of being an imperative model where you tell the data plane entry point and exit point, it's what is called a declarative model. You tell the data plane, I want this object or whatever. I'm sorry, was that a question?
Easier that way.
So I assume since we're moving everything down to the hypervisor level that the compute nodes need to be directly attached to an external network to access the provider network. We no longer have to do that in a central place.
So
Is that accurate?
there's multiple layers to this question and answer. So first of all, yes, so we move everything within the hypervisor. So a lot of the feature and functionality will be implemented within that layer. And NAT, for example, will have one direction of NAT being implemented within the hypervisor layer. Remember, there's always the gateway. So the gateway is really the component that we leverage to exit from this overlay infrastructure out into the legacy network. And this gateway doesn't mean that it's a single device. It can be a cluster of gateways. So again, another layer where we distribute. That's where, for example, the reverse direction of NAT hits. It's where you have, again, another layer of distributed NAT handling the inbound flows and understanding, okay, this packet is coming in with this IP and it has to get to this destination compute node, which sits, it's somewhere in my cloud infrastructure, and I'm gonna use the overlay network to get to that environment. And then based on the implementation of NAT, I know that I have a VM, so I need to do some formal translation to get it to that final destination VM. So NAT really is, in the PLUMgrid implementation, what Fernando was referring to, it's fully distributed, and we kind of have this topology, what we call rendered, meaning the topology is available both in the compute layer as well as the gateway. And the gateway is really the one that is physically attached to the external network.
Do you have, for example, PGP gateway? With inter-domain communication. With inter-domain communication, do you have a PGP gateway?
Another example, another way to look at this architecture, for those of you that are coming from a networking background that are used to deal with distributed switches or routers, your classic chassis, right? You have control modules, you have line cards, right? In one of these. Well, another way to look at this architecture would be your directors, your brains are kind of your supervisor, your control module, that's where your protocols run, your BGPs, OSPFs, spanning trees. And then you have kind of line cards into every server. So your server is processing the traffic. Your traffic is not hitting the control plane, your traffic is going from IO-visor to IO-visor, from IO-visor to external wall. So that entire thing, that entire picture is kind of like your distributed system. If you want to connect to an external router, you would connect it to the gateway. So the inside of the data center, your existing switches, routers, whatever Cisco, Juniper, Brocades, Aristas you have, are actually your backplane now. It's transport. For us, it's transport. We're creating tunnels on top of that. We don't really care what you're running there. Now, if you want to connect to a different cloud, normally you would connect through the gateway. And that gateway can take you directly to another OpenStack cluster, or it can take you to your MPLS-PE and get you into a VPN, or it can get you to your Ironic physical servers, your peripheral servers controlled with Ironic. Your real world outside of OpenStack is connected to the gateway. And inside the gateway, what you have is this virtual switch, virtual router that connects VMs.
And just to add something to the NAT or gateway question, what is important about leveraging, for example, virtual domains is that you have a much better consumption of IPs, a much lower consumption of IPs, because you don't need to have a real IP per compute node. You can have one IP per virtual domain if you need that, and then that kind of gets maxed through the overlay implementation. So long conversation again, but better utilization of IPs and NAT is actually one of the features that a lot of our customers are using us for. Like, if there's one feature that I could name, it's certainly distributed NAT. A lot of interesting use cases you can do once you have distributed NAT.
Yeah, I don't know, but hold on.
There's a mic somewhere. With an architecture like this, obviously the gateway can provide this function for egress, but what about intra or inter-tenant monitoring the tapping? How would I do that?
So if tenants need to communicate with each other, it depends what the design you have. If you go through kind of what we call a service virtual domain, a service virtual domain is nothing but a logical construct. So what you would literally do is you would go on the UI or through OpenStack or whatever you want to build it, and you would just create two virtual domains, and you would create a third virtual domain on top and interconnect them. And I can show you a picture as well. Now, what that means is that inside your compute node, you will have the representation of the two tenant virtual domains as well as the service virtual domain. So inter-tenant communication doesn't necessarily have to go through a gateway or through any air-pinning network node or any component there. Everything stays within the hypervisor layer if the VMs are sitting within the same server.
How do I
How do you?
How do I audit that, like from the monitor?
So there's all sort of things that we built into this product, from real-time analytics to the ability to tap into any VM and kind of look at the real-time traffic coming out of that VM, the ability to trace packets through a virtual domain, and so on and so forth. So there's a very powerful suite of operational tools that we have built as part of the product to help you. I think this is how you operate it, especially when you have a physical and a virtual layer. It's fundamental.
Yeah, just to add very quickly, the other thing we're looking at is a virtual tap as well, so that you can actually have a span point. That was looking for.
I have a follow-up question. You pointed out how your solution is different from Open vSwitch, and I understand that. So you put more knowledge, in effect, topological knowledge of each of these distributed kernel modules in each compute node. How do you deal with the potential explosion of information that needs to be exchanged among the compute nodes for a very complex technology as it scales?
Yeah, so very good question. So a couple of answers to this. So first of all, a lot of the intelligence of these systems it's stored in the control plane infrastructure. So something that PLUMgrid did, we custom built all the control plane components for large-scale cloud solutions. There is obviously uses for generic off-the-shelf components, but we felt exactly for the reason you're bringing up that there's a need for a very robust infrastructure to be able to store information in a distributed, resilient way. So all of the algorithms and technology that we run at the control plane level that enables us to run a distributed cluster with 3 nodes where one can fail and all the information will remain in the system and so on and so forth. That's a very big, important part of our solution. Now, at the data plane level, the way things work is what I was mentioning earlier. So everything in the system, in the PLUMgrid system, is event-driven. And this is fundamental. What this means is that at the beginning of time, there is nothing pushed into the compute layer. Everything is empty, everything is brand new and fresh, like a blank slate. Every time VMs come up, based on the events, we populate the necessary information down. What this means is that you might have, how many? 20 VMs, 30 VMs, 15 VMs, whatever the number is per compute node. That's the amount of information that we push down into the kernel. And the actual implementation of this topology, what we call plumlets, are extremely efficient in terms of consumption of resources within the kernel layer. And so we don't just bluntly populate everything you need out there, only everything that is relevant to that specific local node, it's pushed down. And again, back to Fernando's analogy of the line card, it's exactly how it works there. We only have the information that is needed to then look up a destination and send it over the backplane of your distributed chassis and send it to the destination line card. So we're very efficient in terms of what type of information we push down into the kernel itself. That's very important, yeah. Any other question? Yes?
IPv6 support for all this?
Yeah, we do not currently support IPv6. It's in the roadmap, something that a lot of our customers are obviously asking us about, but that's not something that we are currently supporting. So we can take more questions. I just wanted to give a chance to Fernando to share while we take a couple more questions, just a couple of minutes, then we'll give it to Josh. I think we talked about all of this, things distributed, blah, blah, blah. So let me, let me give it over to you. And
we have very little time, so in order to make sure that I don't go over my time, I'm actually going to play a CAD demo. So this is actually a recorded video, but I have the demo running on my laptop. If any of you guys want to see that, I'll be happy to show that to you. What you can see on the right side is the PLUMgrid platform. And again, this is what runs under the hood. So on the left side, you're going to see an OpenStack, a standard OpenStack window. So when in OpenStack you tell Neutron, hey, I want a network, or I want a router, or I want whatever, then the PLUMgrid platform creates that dynamically. Your script. That's it, no problem. So what you see here is a Python script calling Keystone, Neutron, and Nova. This is going to create networks here, and this is dynamically going to create also a tenant in PLUMgrid that is going to create all the networks that you guys are seeing popping up here automatically are going to be created dynamically in the PLUMgrid platform. So this is the way that you guys are consuming networks today. If you're running PLUMgrid, you're running OpenStack, this is what is going on under the hood. So as you guys can see, this script is creating a full set of networks and tenants, and anything that Neutron understands is being created dynamically in the PLUMgrid platform. That means that all these networks, all these network elements are going to be rendered dynamically into the kernel of the compute nodes that have any virtual machine in this topology. And the other thing that we did is what most people call NFV, Network Functions Virtualization. So once we have created the networks and the routers that OpenStack knows about, we want to create routers, firewalls, VPN terminators, load balancers that are running on virtual machines. So in this case, we're going to create virtual machines that are running Viata and OpenWRT, and we automatically configure them on the fly from vanilla images. We're able to configure everything in those VMs. So the IP addresses, the security rules, the names, everything. So we create an underlying infrastructure of PLUMgrid components, and then on top of that you guys are seeing here, we start creating VMs that are hosting routers, firewalls, load balancers, anything that we want to create. What you guys see here is a connector. This is something that is not existing in OpenStack. As you guys can see, I remember someone was asking, how do we interconnect tenants? Well, how do you interconnect tenants in OpenStack? Tenants in OpenStack are not supposed to be connected. You need to connect them through shared networks or through external networks. Well, our platform does many more things that OpenStack user does not know about. This is one of the things our platform can do. Just connect to tenants trustworthy. So make a network of between two tenants, and we're doing that here. So what you guys are seeing here is the script creating a VM dynamically. As you guys see, this is a Viata VM. If someone is familiar with BIOS, we're putting up a Viata VM, configuring that on the fly, so that when the router comes up, it's already configured with the router name, with the IP addressing, with these two routers are actually running VRP. So this is just to show you guys how, first, PLUMgrid implements everything that OpenStack knows about. It also implements some other features that we do have in our platform that OpenStack is not supporting today. And also in a network functions virtualization environment, we can use OpenStack to create virtual machines running other networking functions, third parties, right? We could be running F5 load balancers, Radware load balancers, checkpoint firewalls, Palo Alto firewalls. And we can create them on the fly, configure them on the fly, and they pop up automatically, configured, okay? So this is a classic use case for these topologies are, for example, for telcos. They want to run underlying routing and switching infrastructure, and then on top of that, they want to call their Cisco's, Junipers, or Ericssons, and run virtualized versions of the devices that they're running in hardware, okay? So this is basically what the demo is about, creating underlying infrastructure that OpenStack knows about, and creating on top of that virtual machines that are already configured with that. Again, we have that running on the net. I can configure that on the fly if any of you wants to see the real demo instead of this quick recorded video. We're already going
way over time.
We're already going way over time. But if any of you is interested in NFV and network functions virtualization, or wants to see how we actually under the hood implement on a distributed fashion what OpenStack does, what the Neutron API knows about, just ping me and I'll be happy to share. Any questions on this, or any questions on the demos? I think we've stolen enough of your time. So,
We've got till 10.
Who's that?
We have till 10 o'clock. So.
Okay. All right. So, thanks everyone.
All right, so I hope this session was helpful for you. I know we went very deep, very quick. Some of you had some very good observations. We'll be around, so happy to discuss more. I'm very passionate technologist, as you could have said, probably, but so I'm happy to chat more with all of you. Sure.
Who are some of your customers? What are some real true-to-life experiences that you've had?
Yeah. So that's a very good question. Again, I'll try to keep it short because for the sake of not stealing too much time from Josh's presentation. But we work with a variety of customers that have different use cases. A good example for us is those that are building public cloud solutions. So large hosting provider, cloud providers that are now starting to offer services on demand. The power of what PLUMgrid does is that we enable them to create this and offer these very rich multi-tenant environments on demand. When Josh goes through the presentation, what we do with some of our customers are building platform as a service kind of offerings. And what we can do is we can very easily configure the virtual domains to match the requirements of Cloud Foundry. So Cloud Foundry has some very specific requirements in terms of some components need to talk to each other, but some components need to be isolated, and I need to be able to access this API layer, but the tenant's infrastructure needs to be So what we can do is create virtual domains that match that requirement and just deploy them on demand in software. So that's one example. We worked with enterprises that are building IT as a service internally. Helping them remove these 75 tickets that they need to open to do any sort of operation in their environment to going to a place where they can just self-service provision something through OpenStack. NFV kind of use cases, so communication as a service. We work with retail customers that are building retail clouds where the ability to, again, efficiently use IP addresses and provide NAV becomes the #1 requirement. So a very wide variety of applications and use cases that we can satisfy. The beauty is that you can customize your virtual domain, so pretty much the sky is the limit in terms of what you can do with it.
For sure. Thank you.
All right. Thanks a lot.